Welcome back to Reconstructing Gravity. This is Ted Cole again, and this is Chapter G9 called Starlight Bending. In this video, I'm going to show you a calculation of the bending of starlight by the sun's gravity. But it's going to be done with our constructive model, and it's going to be done in Euclidean geometry. But the results match very closely to Einstein's prediction. Einstein had predicted that the gravity would bend light. And for the experiment of starlight being bent by the gravity of the sun, he predicted a certain amount of deflection. In 1919, that correct amount was confirmed by experiment, by observing position changes of stars during a solar eclipse. Now, I think it's important to discuss for a moment the different calculation methods used. Einstein, of course, was using his General Relativity theory of spacetime mathematics. It was an analytic method, and it used very complex Riemann curved geometry and no computers in 1910s. And here, in contrast, I'm going to use our constructive model in which space moves following the solar escape velocity function. And the method is going to be, instead of analytic, it's going to be a time-step numerical method. But I'm going to use Euclidean geometry, normal geometry. And of course, I'm going to use a computer. Engineers and scientists are well familiar with this, but for others who might not be, I want to differentiate what an analytic solution is versus a numerical solution. An analytic, suppose you had this function and you wanted to determine the area under the function. Well, the analytic approach would be to use calculus. The calculus essentially gives you a formula you can plug into, and it gets an exact answer for the area under that function. In a numerical calculation, instead of doing the calculus, you'd simply look at the function and do approximations. You'd measure the area under various sections of the curve as shown and add them all up. And if you wanted to be more accurate, you'd use smaller rectangles, not as wide, and then you'd get a closer approximation. So that's a numerical approach. Now back to our starlight problem. Of course, starlight starts as a spherical wave of light radiating from a star, but after traveling over enormous distances, that wavefront is virtually a flat line. And here's the basic setup of our problem. This flat wavefront of light will come to our solar system. Some of it will pass right by our sun, and if the alignment is correct, that light that passed right near the sun will get to Earth. The question is, if this light passes nearby the sun, will it be deflected by the gravity of the sun, and if so, by how much? The key to understanding how much the light has deflected is the angle at which this wavefront approaches the camera. It comes in at a certain angle, it makes a certain spot. That light is focused on a particular spot on the film. But if the wavefront comes in at a slightly different angle, then the light will be focused on a slightly different spot on the film. This was first done in 1919 during the solar eclipse, where the sun's blocked out by the moon. And you can see, the starlight appears to come from a different direction when it gets bent. And here we have a really cool photo of overlays. The stars have to be photographed when it's not during the solar eclipse to get their true positions, and then overlaid with during the eclipse to get their shifted position. Very cool photo. Now, it's a difficult experiment to do, but partly because the solar eclipse The amount of shifting that Einstein predicted was 1.75 arc seconds. An arc second is 1/60th of an arc minute, and an arc minute is 1/60th of a degree. So 1 arc second is 1/3600th of a degree, very small angular shift. We're going to have a wavefront of light passing through space that is moving like this. For my calculation, I'll start with a vertical wavefront that's 5 astronomical units on the opposite side of the sun. The astronomical unit is the distance between the Earth and the sun. So we're going to start beyond the sun quite a distance, and then let the wavefront come towards the sun, pass close by the sun. And the question is, how much will that wavefront rotate by the time it gets to the Earth? Another important detail of this calculation is it's a variable-timestep calculation. So we're going to recompute the position of this vertical wavefront from time to time, but initially the time step is going to be over 100 seconds. But as we get closer to the sun, and I'll show a close-up picture here, when we're near the sun, the time step will get down to about 1/10 of a second. A lot more action is happening at that point in time. The bending occurs, and we need more precision on the calculation at that point. I account for 2 effects in this calculation, and this first one is quite minor. The wavefront is passing through space, but the space is moving unevenly. Since this wavefront is going to pass below the sun from our point of view, the upper end of this wavefront is always a little closer to the sun than the lower end, and therefore it moves slightly faster than the lower part, and that causes a very small clockwise rotation of the wavefront due to this uneven speed towards the sun of space. And this happens primarily while approaching the sun, and it's a minor effect. The second effect is much larger, and it only occurs primarily when close to the sun. And that is a gamma slowing of the wavefront progress, because the end of the wavefront that's close to the sun has to pass through space, which is traveling faster than the space is traveling at the outer part of the wavefront. So therefore, the closer part of the wavefront moves ahead more slowly, and this causes a counterclockwise rotation of the wavefront when passing nearby the sun. Both of these effects are computed for every time step. The resultant rotation depends on how close to the sun the wavefront passes it. The closer pass obviously will produce more rotation. How did this calculation turn out? Pretty darn good. I got 1.64 arc seconds passing close by the sun versus Einstein's prediction of 1.75 arc seconds. That's not bad. It's a little over 6% difference. Now, here's a very exaggerated depiction of the motion of the light path. The blue line is the result of this calculation, greatly exaggerated, but it does show the clockwise rotation approaching the sun, and then the strong counterclockwise rotation right when passing the sun. And again, when going away from the sun, another small amount of clockwise rotation. So those effects are clearly happening. There is another thing in this graph, the red line. When the first solar eclipse experiment was done, Einstein had made this prediction, and they thought there were 3 possible outcomes. 1, no starlight bending. Einstein would be wrong. Starlight bending, according to Einstein, okay, that would be close to the blue line in my calculation. There was another possibility that what was at the time called a Newtonian result, which would be half of Einstein's result, which was a simple v squared over r acceleration towards the sun, similar to what a mass particle would do if it was traveling at the speed of light. And so I put that in my calculation too, and sure enough, that produced half the angle of rotation of the calculation that I did for light bending. So that's just another confirmation of this light bending in this model is quite close to Einstein's, definitely more than that Newtonian model. We've shown this model works very well. If we assume that space, which is a physical medium that transmits light, flows towards large masses at the escape velocity of that mass, we've had success with gravitational time dilation in my video G3, showing how and why mass drops at acceleration g in video G5, and in this video, starlight bending. Excellent results on those 3 tests. There's one more validation test I have to present called the Shapiro delay experiment, another cosmological test of Einstein's theory, which we'll calculate also. But I'll definitely be returning to the flow issues, which we've discussed before. And so far, we've only talked about external flow outside of planets. But there's also a lot to do on internal flow inside a planet or a star. And that is even more difficult and challenging, but also revealing of the ultimate source of gravity. So we got a lot more to do. Really looking forward to presenting it. But that's it for today. Thanks for watching. Please like, subscribe, share, comment. Hope you like this one. Outro music, Crosby, Stills, and Nash, Southern Cross. Catch you next time.
When you see the Southern Cross for the first time, you understand now why you came this way. 'Cause the truth you might be running from is so small, but it's as big as the promise of a coming day. So I'm sailing for tomorrow,